This is the last segment on our lesson on learning to name compounds and write formulas. And before I get into it, really, I want to take just a minute and look at the difference between ionic compounds and molecular compounds so that we can talk about the difference between empirical formulas and molecular formulas. Now, in an ionic compound, we don't really have individual molecules. What we have is bazillions of positive ions and bazillions of negative ions all clumped together and attracted to each other. Sometimes that's referred to as a lattice. But if you had a piece of sodium chloride that was this big, it would all be like one big giant molecule. In fact, sometimes it's referred to as a giant structure. So it does not form individual molecules. All the ions just clump together. So it's not really possible to write a formula that tells us with subscripts the number of ions in a molecule, because it doesn't do that. So what we do instead is figure out the ratio of ions in that big giant structure. And maybe it's a 1-to-1 ratio. If the positive ion and the negative ion have the same charge, then they will be present in a 1-to-1 ratio. So one example of that is sodium chloride. We have a positive 1 ion and a negative 1 ion, and so they will always be present in equal amounts. So we don't see any subscripts here because they're both 1, and the 1 is simply understood and not shown. We could say magnesium oxide, like that. So this is a positive 2 and a negative 2. And as a matter of fact, if you did that crisscross method that we talked about before, you would get a 2 and a 2. But we'll reduce that down and just show it as a 1-to-1 ratio, since it is a 1-to-1 ratio. So we're just looking for the lowest whole number ratio. And that is called an empirical formula. Now, in contrast to that, if we have a molecular compound, those do form individual molecules. And those molecules are held together with bonds where there are electrons being shared. So let me give you an example of CO, for example. So carbon monoxide, the carbon and the oxygen are sharing some electrons. So this molecule will be separate from another carbon monoxide molecule that might be over here, and another carbon monoxide molecule that might be over here, and that's a gas, and they're going to be all over the place. And those are not necessarily stuck together, particularly if they're gases, they're not stuck together. But this tells us the exact number of atoms that are in the molecule. And we can do the same thing with something like water. So H2O, even though that's a liquid and those molecules will be close together, our hydrogen and our oxygen, let me show you what you learned to do already. You learned to do this. Oxygen, 1, 2, 3, 4, 5, 6. Hydrogen, and those become bonds where electrons are being shared. Now, these 3 atoms are being held together by these bonds where electrons are being shared. We might have another water molecule here, and another one here, and another one here, and another one here, and they're all close together because they're a liquid, but they are not bonded together in the same way that these 3 atoms are bonded together. So we call this a molecular formula. Because it actually tells us the exact number of atoms. And sometimes you can have molecules that can be reduced. For example, you might remember from biology something called glucose, C6H12O6. So every glucose molecule has 6 carbons, 12 hydrogens, and 6 oxygens. So this formula is a molecular formula because it shows us exactly the number of atoms that are in the molecule but it's not an empirical formula. We can write an empirical formula. We can do the lowest whole number ratio, and it would be CH2O. So that's an empirical formula that we can write, but it doesn't give us very much information because it doesn't tell us the actual number of atoms. All right, so let's then continue. And we have one more thing to learn about ionic compounds that I didn't give you the last time because I thought I kind of gave you enough the last time to keep you busy. But we didn't deal with this idea of transition metals. Transition metals are right in the middle of the periodic table. We have these two columns over here that we called 1A and 2A, and then there's a big chunk that are all the B columns, and then over here we have 3A and 4A and so forth. Well, this big chunk in the middle are called transition metals. And the thing about those that makes them challenging is that you cannot simply look at their position on the periodic table and find out what the charge on the ion would be. In fact, many of them can form different ions. For example, iron can be a +2 charge sometimes, and it can be a +3 charge sometimes. So if we're going to write the name of a compound, we have to designate what's the charge on that ion so that if somebody looks at the name, they will be able to then write the formula for the compound. Because if you remember, if you look at a name and you're trying to write the formula, you have to know what the charges are on the ions in order to get the subscripts. So if you're looking at something like iron and you don't know if it's a +2 or a +3, then you can never get to the formula. So we designate that with a Roman numeral. So if we were to write the name of this ion, it would be iron 2. Sometimes that's put in parentheses, sometimes not. I don't really care if you put it in parentheses or not. And this is iron 3. So this is the name of that ion, and this is the name of that ion. And so when I use that in a compound, I have to use this whole name. So let's try a few examples. Let's try, for example, MnO2. Let's say I want to write the name of that. Well, I see that my manganese is a transition metal, and therefore I don't know what the charge is on it right away, but it's combined with oxygen. Now we know that each oxygen ion would have a -2 charge, and we can see that there's 2 oxygen ions there, so that means I've got a total of -4 charge. So that tells me that I must have a total, a positive charge there. So if I have a total of -4 over here, I must have a total of +4 here. So that tells me that this has to be manganese 4 oxide. Now let's go back to iron. This is the formula for rust, Fe2O3. So each oxygen has a -2 charge. There are 3 oxygens, so that means I've got a -6 altogether. So that must mean I have a +6 altogether over here. But that +6 is the sum of 2 ions of iron. So each one must be have a charge of 3. Because if this has a charge of 3 and there's 2 of them, I get a total charge of +6. So that tells me that I have iron 3 oxide in this case. Now let's see. Oh, there's another compound, FeCl2. So we know about chloride. We look on the periodic table and it's in group 7A. So we know that each one of those chlorides has a -1 charge. but there's 2 of them, so I have a total of -2, which tells me this must be a +2, and there's only 1 iron this time, so that means that this one has +2, so I can write this iron 2 oxide. So now we have to go backwards. Let's say that we're going to start with the names. Let's do this one. 2-sulfate. These are those pretty blue crystals that you've used at least once already this year. Copper 2-sulfate. So I'm going to start here and say copper 2 must be that. Sulfate, if I haven't memorized it yet, I go look on my table and I see that that's SO4, also with a -2 charge. So using my crisscross method, I would end up with subscript 2 here and a subscript 2 here, because this will come over here and this will go over there. Remember, just a minute ago we said we want the lowest whole number ratio. So that means they're really in a 1-to-1 ratio here. So we're just going to put copper sulfate and call it done. So let's do one more example of this. Maybe we'll have this. So this is chromium. I'm going the wrong way, aren't I? Sorry. Start with a name. Gave it away though. So let's do that. So chromium 3, chloride. Again, this is in group 7A, so we know it has a -1 charge because by this time we got that all memorized. So this goes here, and the invisible 1 goes here, and that becomes CrCl3. So at this point you know everything you need to know about naming compounds and writing formulas. Now you don't know everything there is to know in the world because there's lots of kinds of compounds that we won't be covering in this course, but you know everything you need to know for this year.